Thank you, everyone. Very glad to be here today. This is my first time speaking in an international conference, and I'm very, very happy. And yeah, big thank you to the organizers for having me here. Yeah, I'm going to talk about how debuggers work and how you can build your own one. This talk is targeted towards someone who would be interested in knowing how essentially a debugger works internally, or they would like to contribute to Delve, which is the popular debugger for Goland, vim-go, and VScode. It would also be beneficial if you have never used a debugger and would like to use one. And yeah, I mean, so this is not something which is an advanced level. So if we have any Delve contributors in our crowd today, so definitely not for you. You can walk out. Yeah. Yeah, let's see. Yeah, I am Sayani Bhattacharjee. I work as a software engineer at Truecaller. It's a Swedish company headquartered in Stockholm. I work for their Bangalore office based in India. You can find me on my social, Sayani BH, on Twitter, X, or whatever they want to call it next. Yeah, I'm also Sayani BH on LinkedIn, in case you want to connect with me on LinkedIn. Yeah, so I think we are all familiar with this. We can do a show of hands for people who still use print statements. I do every time. Lot of us, yes, yes. So this talk is for you then. Yeah. Okay, talk to a rubber duck, maybe, sometimes. Take a walk, that helps. Also taking a nap or a shower also helps, I guess. Also, just finding the first link of Stack Overflow on Google and then not finding your answer and then going back and looking for the documentation also helps. I don't know how many of us run the same code again and hope that it works next time. Yeah, but yeah, we are going to actually use debugger and learn how to use breakpoints and what does it mean to actually put a breakpoint and how processes work and yeah, just learn the internals of it. Yeah, so we are going to talk about Delve, not the internal architecture of Delve, but how we can emulate something like a Delve, and if you're interested in writing a side project of a debugger in any language of your choice, then how do you do it? For beginners here who have never used a debugger, I'll just show you a target program, and then I'll walk you through the major features that any debugger would have, independent of whatever IDE that you are using. Also, it's just post-lunch, so all glucose spikes I see. Yeah, so we just have a very simple hello.go here. It's just two functions, one main, one add. We'll see how a debugger works. So this is my IDEs right now in VS Code. My development environment right now is I'm running a Alpine OS on a dev container. I'll tell you why I'm doing it and not building on native macOS shortly. Okay, so let's see. We have a breakpoint at line number 8. So you just click on the side and you can put a breakpoint. A breakpoint, what it means, let's say if we run on debug mode, so it has stopped our process on line number 8. And if we click on the play button here, it goes on the next breakpoint. And if you click on the play button here again, it ends the process. So this is what going through multiple breakpoints mean. A breakpoint is nothing. It just stops a process at that point where you have asked it to stop. Let's remove one of the breakpoints and let's rerun it again. And we are right now at the first breakpoint, and this thing is called, let me just hover this. Okay, yeah, you can see that this is called step over. So a step over means that you're going on the next line of your source code. So if I step over again, it should go to 10. If I step over again, it should not go inside the implementation of the function sum. Perfect. So this is how step over is supposed to work. Let's just see another thing that is also very important in a debugger. Suppose we are stepping over. We are here, right? So there is a function call. So whenever there is a function call, we can step in. We can also step in on any regular line as well. But what happens when we step in on a function line is it goes to the implementation of the function. Then you can step in further, you can step over, and then you can step out at any point to get out at the line of where the function was being called. So this is called step in and step out. Yeah, breakpoint I've already showed, and continuing through multiple breakpoints, we have already seen that. Yeah, that's pretty much what major debuggers support. There are other functionalities if someone is interested. Another popular debugger that exists or most developers use is GDB as well, but we are primarily going to talk about Delve and how you would emulate Delve. Okay. Yeah, so the topics that we're going to cover is how to set a breakpoint. So there are two types of step-in actually. There is a step-in instruction and there is a step-in on the source code, and then there is step over, and then there is step out. All right. So when you have to debug a program, right, like you have to first build or first compile your source code. The Go compiler by default has a lot of optimization. So just now that we saw that when you're actually putting a breakpoint, you're putting a breakpoint on a particular line of the source code. So while compiling, you have to ensure that you're disabling all compiler optimizations and all inlining functions. So you have to build your target file or program with these commands. At any point, you can also see your assembly output to see if there are any like function inlining happening, or if it's compiling correctly or not. So that's another command that you can use. Yeah, so for the program that we just saw, so our source code doesn't really compile directly to a binary. There is like a set of instructions that executes, and when a process is actually executing, it goes through multiple lines one by one of the instruction that you see. So on the left is the source code, and you can see the colors. So, so let's say A equals to 10 evaluates to 2 instructions there, and those are the highlights. And this is not a complete set, so actually the instruction was like pretty long. So this is just a snapshot of it. At this point, it is important to understand that. Let's just go back. What happens when we say that, stop an instruction? So we need to understand that there is something called a program counter. So program counter is something that points to the next instruction that is going to be executed. There are a bunch of registers also which are useful if you want to go very much in depth, like your RBP, the base pointer, or the stack pointer, RSP, or the RIP, which is the instruction pointer. For the sake of brevity, we will just talk about program counter and how to get the program counter at any line so that we can set a breakpoint at that. Okay. Another thing which is very interesting is the DWARF notation. The DWARF notation is independent of language. As you can see that all languages support it. It's just the way whenever a debugger runs, that's how it reads from the DWARF file. The command here is what you would typically use to write the L file. So the L file would have a lot of sections, debug info sections, and a bunch of other sections, which will be very helpful to get at what point your process currently is, or how to go to the next point in the process. The L file is also helpful for reading the symbol table. Now, the symbol table is what consists of the information of where your variables and functions are stored in memory. So whenever you load the program, so how do you know where it exists, how do you know where to modify, where to go. So yeah, that's the information that you get from the symbol table. Okay, so we are here at ptrace now. So whenever a debugger starts, right, and we already spoke about a target file that you would like to debug, the debug server would need to control another process. Let's say if we call the debug server that starts the main process as the parent process, it would actually need control or need to trace the child process. So Linux has this system called ptrace. Yeah, so coming back to why I'm actually building on a dev container here is that so the default macOS doesn't really have all the wrappers essential for writing all these ptrace commands and all. So Linux has that support. So that's the sort of development environment. Like if you're just playing around, then you would need that. Of course, Delve implements it on all the environments, but that's like tricky to do that. So we'll just talk about Linux syscalls and how it happens. So for ptracing and to trace another program, we have a library in Go called this sys/unix package. You can see that there are a bunch of methods here. Some are obviously named. One is ptracecont. So it just takes a process ID and then it continues that process. One is ptrace attach. It takes a process ID and then it attaches it to it, and then you can do and control the attached process. Another interesting thing that you might want to tweak around with is the ptrace getregs. So getregs gets if you give it a process ID, and it actually loads all the registers in memory, and then you can fiddle around with your stack pointer and current frame, and you see how your stack is moving around. We are also going to spend some time with ptrace single step. So single step, as the name is evident, it just does one single step of the instruction. The instruction is what we had actually seen in our earlier slide. So when we do a ptrace single step, it is just going to move the program counter to the next instruction. Not really the next line of the source code, but one line would evaluate to multiple lines in instructions, so it would go to the next instruction level. Poke data and peek data are something that we are going to talk about, and that's also very important for debuggers. Okay, so first step would be that we want to be able to have a parent process which is able to control a child process, and if you are able to do that, then we can build up on that. So I will quickly run. I'll first run the program and then see the output, and then I'll explain what is happening. So if I do go run step1.go. So here you can see that breakpoint was reached. The output of my program was printed, and then the parent process has exited, right? Now let's jump to step 1 and see what is happening. I'll stop this debug mode, and I'll just, for the beginning, I'll just go line by line and explain how a process is started. And after that, we can sort of build on this code. Okay, so we have an input file. We are giving it the binary. You can also get it as a program argument. Then we are starting a process in line number 16, and then we're attaching all the std-in, std-er, and on line number 22, we are actually starting the process. If you omit line number 21, a general process would start without actually having any sort of tracing ability to it, right? But we would want to trace the program, so we set ptrace to true in this sysproc attribute. And then we have this cmd.wait, which actually waits for something interesting to happen. When we actually set ptrace to true, by default, a trap is generated, or an interrupt is generated in the first line of the code. That's like, by default, that happens. After that, we are actually continuing the process, because like on line number 27, the trap would be generated, and from the trap, you would need to continue the process till the end. So line number 33 is where the process is continuing, because we are passing it the PID. And yeah, and we are waiting, and then it actually executed the hello world, and then it said process has exited. So here, this explains that we are able to control, or let's say trace a child process from a parent process. We'll quickly go to step 2. So step 2 is to be able to go through line by line of the process. So in the previous example, we just went, the first trap was generated by ptrace, by setting ptrace true. Then we did the ptrace cont, which ended up taking the program till the last, because no other signals or interrupts or anything else was found throughout the process, right? Right now, we want to go through like step by step every instruction of our source code. So we will run this step 2a.go. So this will just go through, this is counting all the steps. I have a for loop, and then it's going through every instruction of our source code, and then it's just adding a plus. This will actually print a big number, because it also involves all the libc initialization, so it's just not going to be like 10, 15 lines. Okay, it's adding step. Okay, it has stopped the process, and we are able to go through all the instructions of the source code. So yeah, now we know how to go through instruction by instruction of our source code. Another thing that I would like to tell you is, because once we know that we have to go and set breakpoint and continue a process from that point, we also need to know what a symbol table is and how a symbol table can be generated. So from the L file that we had earlier created, we can load the sections here in the get symbol table, and once we get the sim table, we have something called lookup function. So in lookup function, what it does is it takes the package name dot the function name, and then it prints this. So let's just quickly run this. So it says that function main.main is at line 7. Let's just confirm. Perfect. So function main is at line 7. So we can get where the function starts and a bunch of other stuff about a function and about variables. Let's see for any other function. We had 2 functions in our file. So if we run it again, it says that function main is at line 7 and function add is at line 14. Let's just verify that. Okay, so function add is at line 14. Okay, so now we know how to get details of a function. There are, like you can check out what all functionality, yeah, so this is the package that we are using, GoSim package. You can check out what all functionality are available. Here, what we did was we actually gave it the program counter of the instruction that we are currently running to get the line number. There is also something called line to PC, where you can get the line number and then you get the program counter of it. Line to PC is helpful because PC is the one that you want to know if you want to stop it at any random line of your process, right? Yeah, so this is something which you will use. All of this code is available. I'll publish my GitHub repository towards the end of the talk. Yeah, let's get back. Now that we are able to trace a child process, and we also know how to go through line-by-line instruction of our source code. The next thing we are curious about is how do you insert a breakpoint? So inserting a breakpoint is nothing but actually inserting something called a hex-CC. So a hex-CC generates a SIG-trap signal or an interrupt 3. And yeah, if you want to pause process, you have hex-CC. Okay. Now, Linux has a lot of other traps available. What we are interested here is the SIG-trap process. So in case, if you go read around Delph code, or if you are interested in like writing your own debugger as well, so you can at any point check for whether the signal being generated or the interrupt is a SIG-trap or not. Perfect. So in breakpoint, so we said that like hex-CC is the one that actually generates the SIG-trap, right? The question next is that how do we even insert a breakpoint, or how do we insert a hex-CC on our code? So how this is achieved is, whenever we have the program counter, we can go up to that line, and then the first byte, we can like modify it with something called ptrace poke data. This is the man page of ptrace poke data and peak data. So ptrace poke data actually modifies the first byte and then stores the data in any variable that that you give it to, right? So because if you're modifying the first byte of that instruction when you insert the hex-CC, because when your process is executing, as soon as it reads hex-CC, it's going to stop there. So for that, you will need to insert it in memory. So that's how you insert a breakpoint. And because once you've inserted a breakpoint, let's say you have stopped the process, but at some point you would also want to clear the breakpoint and move ahead in the program, right? That's where ptrace peak data is useful. Before you modify the program, you would want to store your original data that you had in the first byte in the address. So ptrace peak data supplies that. And after you have like stopped at your breakpoint, whatever, inspected and seen that it was actually hit the breakpoint or not, you can do ptrace poke data with the original data that you had stored with the peak data thing. This is a bit complex. I'll just quickly show you how the code looks like for this. So I have a step 3. I will, these are just like demo steps that I have made. I have like a complete program that is well structured. So yeah, don't mind the programming constructs if it's not like Go-like. Yeah, so what is of importance here is line number 98. This is where we actually insert the peak data. Let's run step 3 once and see what happens. Okay, so the first trap is reached. We already saw that whenever a process is started with ptrace true, it automatically starts with the trap on the first line. So my program is asking, what do I want to do? So I want to set a breakpoint. Where do I want to set a breakpoint? Let's go. Let's set a breakpoint at line number 9. Okay, so I say that I'm inserting a breakpoint at line number 9. So you can see that the process is stopped at main.main at line number 9 of hello.go. So we have successfully hit our breakpoint. At this point, if I want to continue, so my process is paused at this point. Now, if I want to continue my process from here, I would do something like continue. So continue would just do a ptrace cont and move it to the end of the program, unless, of course, it also finds any other breakpoint on its way. So if we do a continue, perfect. So it has printed hello world, and it has gracefully exited. So now we are able to set a breakpoint at any line, and we are able to continue the process till the end of the line. Okay. Also, just do a quick explanation of how this happens. So the syscall package has something called the ptrace peak data. The Unix sys/Unix package is also useful. I think syscall is no longer being maintained, so please use the sys/Unix package. So when you do a peak data on it, you're actually storing the original data so that you can actually remove it later, okay? And then you modify and insert a breakpoint, and then you return original for whenever you would actually want to remove your breakpoint. So this is like a sample way in which you can achieve inserting a breakpoint and removing a breakpoint. Okay. So we had seen how UI had step in, step out, and step over, right? We will walk through it one by one. This is a rudimentary implementation. It's not like implemented for very complex programs where there are Go routines and defer functions and all of that. Just to build an understanding of if you would like to build your own step in, step out, then how do you go about that? And also how Delve would do it at a very happy case. Okay, so we'll just go close all of these for a while. And I'll go back, and here is my actual debug server that I have written. So it's a small debugger, so I've called it smallerger. Yeah, naming is difficult. So yeah, bunch of things. Let's just do it one by one. Just 1 minute. I hope you can still hear me. Yeah. Just an introduction to the project. I have something called build-all.sh, where I'm saying that I have a target file that I want to debug, and I'm debugging it with by removing the compiler optimization and function inlining. And I'm also generating an L file because I'll need to read the symbol table information and everything. I have another script, debug.sh. So this is actually that is building my debug server. Yeah, let's go back to smallerger, and let's try to, 1 second, did I, okay, all right. So we'll run our debug server. So let's see if we are able to step in or not. So it's asking me, do I want to set a breakpoint? So I will, before that, let me also open up the target file that I'm debugging. I think this would make it more sensible, yeah. So this is the program that we are trying to debug right now. So let me try to insert a breakpoint on line number 11. And I will stop taking breakpoints at this point. Yeah, so you can see that it has printed that the first breakpoint was hit. I would like to continue to reach my first breakpoint that I have put. So now I have reached line number 11 because I had like put a breakpoint on line number 11. So my process is stopped at line 11 now. And now I'll do step in instruction. I'll explain what's the difference in between step in and actual step in instruction. So so one source code, like one line of the source code would actually evaluate to multiple lines on the instruction. So there would be scenarios where if you're doing a step in instruction, it stays in one line multiple times until it goes to the next line. Okay, let's do it again. We're still at 11. Okay, so now we're at 12. And now we have entered 16. Perfect. So it has found a function call, and it has gone inside the function call. And this is what step in actually is. now that we are able to step in, I'll tell you what is the difference in between step-in and step-in instruction and how Delve implements it internally. So imagine a scenario where you have like not such a simple program, but like a very complex functions, nested functions and everything. And if you are actually trying to step in, there is a huge, comment on one of the lines. I'll pull it up later. So step-in internally actually inserts breakpoints in all of the line of your source code. Because there is no other way in which you can achieve stopping at that point. The only way is to actually reach any sort of a trap, and then you go to the next level, and then you go to the next line. So an internal implementation of step-in or step-in instruction is that you set whenever a step-in on your UI is hit, the debug or the delve knows that it has to step in all the lines of the current function. And it doesn't really show you on the UI, so you'd be confused that, okay, it's not really inserting breakpoints in all the lines. But internally, it inserts, it clears the breakpoint on the current line, it goes to the next line, then it clears the breakpoint on that line. And that is how step-in is achieved. Also, it is a ptrace single step, so it goes to single, like if you're doing a step-in instruction, so that's how ptrace single step happens. So you're actually going through line by line of the instruction. If it's not a step-in of instruction, then the only way to achieve it is by setting breakpoints in all the lines of your source code, and then you go jump one by one in all the lines, and that's how, like, it's not an elegant implementation, but that's how at least Delve implements it. Okay, now we'll go to step out. I'll just exit this program and let me quickly try to put a breakpoint at line number 17. And I'll quit taking breakpoint, and I will continue. So continue just takes you to the next breakpoint. Perfect. So we are on line number 17 now, and then we will step out. Okay, so on step out, it should have gone to the line where the function was being called. So we are at line number 12, which means we have been successfully able to step out of our current function. Let's just continue, and then the process is exited. Cool. How step out works is, so once you're inside a function, right, you would want to know at what point, because we are not essentially doing a step out at line number 20. We can do step out at any line from inside a nested function. One thing about how a return address is stored is, return address is always stored 8 bytes from the stack frame. So if you can read the memory, if you can get the current stack pointer and compute your stack frame, then you can read 8 bytes ahead, and then that's where you would want to insert a breakpoint and then move your program counter at that point. Again, there is no other way to actually stop a process. Whenever you're stepping out as well, right? So you're actually going out and stopping at the line where the function was called. For that also, you would need a trap. And how we generate a trap is by inserting a breakpoint. So internally, even step out only inserts a breakpoint at the return address. It goes to the return address, then it continues, and that's how step out is achieved. Okay, so we have seen step in, we have seen step out. Let's see step over now. /debug.sh. Okay, so for breakpoint, I would set it on line number 9, and okay, I have to quit taking the breakpoint, and I will do a step over. If you remember what a step over does, a step over goes on line by line and to the next line of the source code, and if it finds any function call, it skips that function call and it goes to the next line, right? So let's do a step over. Okay, no, first we will, because we have put a breakpoint on line number 9, we will have to continue up to that breakpoint. Perfect, so we have stopped our process at line number 9, and now we will step over. Okay, 10, 11, 13. So actually it skipped the function call. It did not go inside F1 and then step over, and then the processes exited. So one way of doing a very like experimental step over can be that you are just whenever a step over is clicked, let's say from the UI, and then your target layer gets that code, so you could just set breakpoints in on all the lines of the current function, and then if there is a function call, you can omit it and then just go to the next breakpoint. That's not a really elegant way of doing it. How most debuggers achieve it is by seeing if there is a call instruction at that line or not. If there is a call instruction, you actually can get that point by parsing the DWARF file and then skip doing that and put a breakpoint on the next line. Otherwise, it's like you can hard code it, but then if you would want a production grade or like a proper debugger, then that's like one of the ways to achieve it. Okay, so we have spoken about step in, step out, step over, and yeah, this is the code that I showed you. I'll quickly glance over the structure that I have maintained. So even for Delve, there is a UI layer where you do the interactions. Then there is a symbolic layer which talks to all the symbol tables and where you get the information. And then there is a target layer that actually does all the syscalls. So here also we have, I've just tried to structure it something similar where my elf.go is where it reads everything from the elf file, line to PC, PC to line, get details from the symbol table. I also have an input.go that is responsible for taking the input, so you can consider this as the UI layer. Then I have the exec.go. So exec.go is what actually does all the syscalls. So you can see that all the ptrace peak data, ptrace poke data, everything is happening here. If you want to get the program counter, you would get the registers of that, and then that's how registers.pc, you get the program counter. So my exec.go is where all such functionalities are defined. And then I have my actual debug server. So this is my smallogger.go, and this is where I'm creating my process, and I'm calling this bunch of functions, and depending on the cases, we are executing the function. Yeah, I think this is pretty much it. If you would like to go through, you can check out. I'll be implementing a lot more features. This is like a passion project that I have been doing, so yeah, feel free to see, or I'll also blog about it or talk about it on Twitter. The next thing is variables. As you can see, this is one of the trickiest things to do. Because like with the compiler optimization or without, it's very difficult to know where at a point your variables are. Cy Brand has a 10-part article on how to write a debugger in Linux. He has written it in C++. You should definitely go and check it out. This is a snapshot from one of his blogs. Yeah, so I am still figuring out, like I haven't successfully implemented on how to inspect a variable whenever a process is stopped at a breakpoint. But yeah, I'm still like fiddling around. So far, I have read that what you do is you actually parse the DWARF file, and then you see where your current line, what's the instruction and what's the size of the instruction, and then you set an offset on your register, and then you go and set a breakpoint there, and you load it from your register. That's mostly for global variables and constants, but I'm sure it's a bit more trickier. Yeah. So this is Delve, and these are all the commands that Delve supports if you run Delve on the CLI. Delve is also integrated, the UI that we saw, VScode, Goland, vim-go, all of them integrates Delve. On the UI, I don't think they support all of these functionalities. This is in their README on the GitHub page, so you can go and check. There are a bunch of other things also, but these are like the primary functionalities that they have. I think we have implemented continue. We have implemented step instruction, step out. I think that's a very good start for a hobby project. Yeah, so if you would like to go through all of them, or for your interest, if you'd like to implement, then these are the like future improvements that you can think about. Um, okay, we are towards the end. So these are the reading resources that I have referred to. The first one is how do you parse dwarf, and how does how do you get all these symbol tables, and where your variable is, where your function is. So it has a bunch of examples as well, so you should definitely check it out. Writing a Linux debugger is what I was talking about, Cybrand has written. It's a beautiful, beautiful, like one of the best technical articles or blogs that I've written in my life. I've read in my life, sorry. You should check it out. It's a bit extensive, but he mostly covers everything in depth. If you want to start reading Delve and understand or contribute to Delve, I would recommend that you start with this file, because it starts with a very big command on how step in and step over actually is implemented. Why you would need to insert a breakpoint, because it's very unintuitive that you would do it, that you would have nested breakpoints and you would clear it, and then all of that is not really intuitive. So that's a good starting point. Or how you can also read Delve is that the commands that I showed, you can just grep for these commands in the Delve repository, and they have like switch cases for all of them, and you can go and read one by one. It gets a bit difficult when the syscalls are involved, but yeah, I think you'll be able to read after you have gone through this. This is the README for Delve, if you're interested in contributing, or if you're interested in just in like a hobby project, if you want to read more, yeah, you can do that. Thank you. That's all there was about debuggers. I hope you have learned something, or you're interested in debuggers and would like to go back and do some peek data and poke data today. Yeah.